then I claim that this means that integral over C, and I mean any, and here I mean really any closed curve anywhere. If I have an integral over some curve C, this will be equal to the integral of the curve C prime as long as they have the same endpoints. Right? How would I prove this? Well, so here's my curve C, and here's my curve C prime. Right? So this is C and this is C prime. So to prove this is the same as to prove that this minus this is 0. Right? But what is this minus this? It means that I go like this, but then I change orientation on this one. So I go, so this is minus C prime. It's going like this. So it means I go like this, I go like this. And these two curves together combine into a closed curve for which the integral is 0. You see, that's how I get that this is 0. So C minus C prime is a closed curve. Is this clear? Any questions about this? How many people have followed this argument? Raise your hand. Okay. How many people have not followed this argument? Don't be afraid. Everybody, you didn't? Not quite. Okay, so what's the sticking point? Right. So now, this argument was clear that why the integral over the closed curve is 0, because you have the same initial and end points. So what I'm trying to explain now is that suppose I have an integral, suppose I have a vector field such that for any closed curve, the integral is 0. I want to demonstrate that in that case, the integral over any curve, even with boundary like this, would necessarily be equal to the integral over any other curve with the same boundary. In other words, I would like to derive this formula from this formula. And the way I do it is I say, okay, what is, so I want to show that this is equal to this, but it's the same as saying that this minus this is 0. Okay? And now I explain that the difference between these two integrals is actually could be thought of as an integral over the curve, which is C, the original one, this one, minus C prime. But C minus C prime is actually the closed curve. So since I had assumed that for all closed curves it was 0, this implies that this difference is 0. So this was just to say that these two properties are actually equivalent to each other. So you should not think of this corollary 1 and corollary 2 as two separate statements. One is path independent. One is path independence. The integral is the same over all paths with the same endpoints. The other one is a statement that the integral over any closed curve is 0. And the point is that these two statements are equivalent to each other. Okay? Now, so where does this leave us? So we see now that if you have a conservative vector field, things simplify. Let's just put it this way. Things simplify a lot. So of course then the next question is, how do we find out if a given vector field is conservative or not? Because if it is conservative, we can apply this and we have all these nice properties. And if it's not, then we have to use other methods. So this now is really the question. How do you determine whether f is conservative? And if it is, how to find a function f such that this vector field is the gradient of that function. That's the question. So as a warm-up, let's observe one property of conservative vector fields. So we are given, let's suppose that f is conservative. So f is pq, and let's suppose that it is conservative. So it is nabla f. So in other words, let's start from the other end. Let's suppose it is conservative. What can we say about it? What kind of properties does it have? Say again. If it is conservative, then f of b minus f of a is a line integral. Right. That's the formula to have. But this is still way too abstract. First of all, we talk about some curves and things like that. I would like some very simple algebraic criteria where I don't do any integration, but just look at the components pq, and I would like to have a criterion to say whether it's conservative or not. Yes. Does this have a proof? Are we going to prove it in this class? Well, I was hoping to prove it in this class, but I may run out of time today. So the proof is very simple, and it's in the book. The proof is follows almost immediately from the fundamental theorem of one-dimensional calculus when you just spell out what this means. In other words, when you parameterize the curve and substitute everything, you just you get on the nose the fundamental theorem of one-dimensional calculus. Okay. So I would like an algebraic criterion. You see, I would like an algebraic criterion which does not involve any curves or any integration. So see, what does this mean? This means that P is f sub x, and Q is f sub y for some function y. So here's what I can do. I cannot compare these two guys because a priori, the two partial derivatives are a priori have nothing to do with each other. But what I can do is I can kind of equalize them in the following way. I can take P sub y. I can take the partial derivative of P with respect to y. If I do that, I get fxy. Right? On the other hand, I can take Q sub x. That's a partial derivative of Q with respect to x, and that's fyx. Right? So now remember, our good friend Clairaut told us that if you have a function which has continuous first partial derivatives, then it doesn't matter in which order you take second partial derivatives. That these two things are actually equal to each other. They're equal to each other. So what does it mean? It means that if your vector field is conservative, this property will necessarily have to hold. In other words, P sub y will have to be equal to Q sub x. So that's a very simple. Maybe I keep this, but I. So we conclude that in this case, P sub y is equal to Q sub x. Or if you will, dP dy is equal to dQ dx. Here's an example. So let's say the vector field is y e to the x plus sine y times I plus e to the x plus x cosine y plus 2y j. So this is P, and this is Q. So let me ask you this question. Is this vector field conservative? Okay. So in other words, conservative would mean that there exists some function, there is some function above it, such that you get this by taking f sub x, and you get this by taking f sub y. It's very difficult to guess right away. Just by looking at those two functions, it's very difficult to guess whether such a function f exists, you see. Because it's like you should be able to extract, in some sense, the antiderivative in x and y and see that the result is somehow the same. Right? But now we have a very simple criterion as to whether it is conservative or not. Because we can argue as follows. We can say, well, if it is conservative, then dpy would have to be equal to dqx. Are they equal? So, natural question, are they equal? So let's calculate. What is dp dy? dp dy is e to the x plus cosine y. Everybody agrees? What's that? Yes? Okay. And now dq dx is e to the x plus cosine y. It's the same. Okay? So there is a chance that it is conservative. I have not yet, so far what I've said is that if the vector field is conservative, then this has to hold. And we see that they are equal. So there is a potential, there is a possibility that this vector field is in fact conservative. But it turns out, in fact, that in this particular case, this is not only a necessary condition, but it is a sufficient condition. And this vector field is in fact conservative. So how do we, what is the precise statement, and how do we find this function f in this particular case? So, by the way, for this particular vector field, then, it would be very easy to calculate its line integrals. You don't need to parameterize anything, any curves, and so on. You just find this function f, and you evaluate that function at the endpoints. For example, if there are no endpoints, if it's a closed curve, you know the answer is 0 right away. See, so it's a, I'm sorry, how to find the function f? I'm getting to this. No, you haven't lost anything. Okay, so what we've established so far is that if f is conservative, then dp dy is dq dx. In other words, this statement implies this statement. But actually, the claim is that the converse is also true. That if this formula is true, dp dy is equal to q dx, then there exists a function f such that the vector field is a gradient vector field. Under one assumption, the converse is also true. Under the assumption that the vector field is defined on a region which is simply connected. Region in R2. When we talk vector fields are defined on the plane, right? So it's defined on a region in R2 which is simply connected. Simply connected. So I have to explain what simply connected means. Simply connected simply means, it doesn't simply mean that it's connected. It's a different property. So you see, connected is easy. Connected means that this is disconnected, right? This is disconnected. This is connected. So this we know. That's easy, right? Connected means there's only one piece. You cannot separate it, the object. But simply connected is a slightly more sophisticated property. So, well, I drew it in the case of two-dimensional region. But if you want, since we talk about one-dimensional objects, curves, maybe it's better to just talk about this curve as opposed to the curve which is a union of these two, as opposed to the curve which is just this one. So this is connected and this is disconnected. But simply connected region, it's true in both settings. It's true for curves, or it could be true for regions like this, as you like. But simply connected something more complicated. Simply connected means that any curve that you can draw in your region. So let's suppose you have a region like this. Simply connected means that if you draw any curve in this region, like any closed curve like this, you can deform it so as to, under deformation, it all collapses into one point within the region, right? So in this particular case, I can deform it. I can make it smaller, 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 and like this. Okay. Now contrast this to the case of a region which has a hole. So it's like annulus. Right? So in this case, if I take this loop, I cannot deform it continuously to a point. I cannot collapse it into one point because I can make it smaller, all right? I can make it even more smaller, but I cannot pass through this hole. You see? So simply connected, put in the most down-to-earth terms, is the region which doesn't have any holes. And the hole actually, even if it's just the region with one point thrown away, it's already non-simply connected. So this is simply connected, and this is not, and this is not, because even here, because this point is thrown out, I cannot pass by this point. And this turns out to be the only obstacle to the converse statement, which is kind of it's really a mild restriction, because to begin with, most of our vector fields are actually defined on the entire plane, right? For example, this vector field is surely defined on the entire plane. In other words, you can put any x and y and it makes sense. The formulas make sense, right? So, and the entire plane is certainly simply connected, right? So, or any disk on the plane is simply connected. It's only when the vector field is not defined at a particular point, or is not defined on a, there is some hole like this, that you cannot apply this result, you see. In fact, in the homework, in one of the exercises of the homework, there is an example of a vector field on, which is defined on a non-simply connected domain, for which what we're going to do now does not work, for which this implication this way does not work. So this is explained in the book. Yes. Very good point. So these are actually connected. These are all connected, right? Because it's only one piece. I cannot separate it into two pieces. It's only one piece, right? So that's why I talked about connectivity first, because I wanted to emphasize that actually these are two different properties. You can have a connected region, but non-simply connected. Okay. Let us assume, though, that our vector field is defined on a simply connected domain. For example, this vector field is, because it's defined on the entire plane, and the plane for sure is simply connected. Then I claim that actually the converse statement is true, which means that if you know that dp dy is equal to dq dx, which is what we actually found to be the case for our vector field, then there exists a function f so that our vector field is a gradient of that f. So now the only question remains is how do we find this f, right? And that's done by a very simple algorithm, where we simply take antiderivatives of this component of the vector field, an antiderivative of the component of the vector field. So let's find f in our example. So what I'm going to do is I'm going to take this p, and I'm going to take its antiderivative. Because p is, so we're looking for function f such that this is derivative with respect to x and this is with respect to y. But if so, we should be able to find f by taking antiderivative of this with respect to x, right? So take antiderivative of p with respect to x. What do we get? Well, so in other words, with respect to x means that we treat y as a constant, not as a function, not a variable, but as a constant. And x is a variable. So when we take the antiderivative, we get y e to the x plus x sine y. Don't be surprised that you get x sine y, because even though it's a sine y, but it's a sine of y which is now treated as a constant. So this is treated for all intents and purposes as a constant with respect to x. So we just put an x in front. That's what gives us the antiderivative. Now, if we were in one variable calculus, we actually wouldn't stop here. We would write a constant. Right? This was very important to always remember that you can always write a constant. Why? Because when you take a derivative, constant disappears. Right? So there isn't a unique antiderivative. There is an antiderivative up to addition of constant. But now we have two variables. So this should be a constant with respect to the x variable, but it may very well depend on y. So what we should do, the only difference from the old calculations is that you should put dependence on y. And now we find this function of y by comparing to the result for q. I mean, calculating the, so we sort of go zigzag like this. We start here, we take antiderivative, but we get some indeterminacy. So we resolve the indeterminacy by going back to the second derivative, to f of f sub y. Right? So let's take, so the first step is like this. Second is differentiate with respect to y. What do you get? You get e to the x plus x cosine y plus c prime of y. That's what we get. But this is what we should get. We should get e to the x plus x cosine y plus 2y. So we recognize that the first two terms have appeared. And now we want to find what is c prime. Well, comparing to the formula for q, we find that c prime is 2y. And that means that c of y is y squared plus a constant, which is now a known as constant because now we are dealing with a function in one variable, right? So the answer is this function plus y squared plus a constant. And that's how you find the function f for conservative vector fields. All right, so we'll continue next time. Have a good weekend.